Welcome. In this explainer, we're diving into a research paper that tackles a massive problem in data science. How in the world do you find meaningful patterns when you're drowning in information? Let's break it down. So here's our roadmap. We're going to start with the core problem that modern data creates. Then we'll look at a really clever way to approach it, introduce the algorithm that makes it happen, and finally check out the results and talk about why this all matters. All right, let's jump right in. To really get what this paper is about, we first have to understand the challenge it's designed to solve, trying to find groups in data that has tons and tons of variables. So, what even is clustering? At its heart, it's just about finding natural groups. Think about sorting your customers by their shopping habits, or astronomers grouping galaxies by their shape. It's a foundational tool used absolutely everywhere. But here's where things get tricky. That simple idea of grouping things, it starts to completely break down when we have what's called high-dimensional data. And this leads to a notorious problem known as the curse of dimensionality. So what does that actually mean? Well, as you keep adding more features, more dimensions, the data gets incredibly spread out. It's like points in a vast empty space. Everything starts to look equally far away from everything else. And if nothing seems close together, how can you possibly find a cluster? It becomes almost impossible. And here's the real kicker. Your first instinct might be to just get rid of some of those dimensions. But the most common way of doing that can actually be a trap. You often end up throwing out the very information that's most crucial for telling the groups apart in the first place. So, you see, the point isn't just to chop down the number of dimensions we're looking at. The real secret is finding the absolute perfect perspective, the right angle to view the data from. And this brings us right to the central question this research paper is trying to answer. How can we intelligently pick a specific, lower dimensional view, a subspace, that makes those hidden clusters just pop right out? The paper's key insight is really clever. It borrows an idea from a classic method called Fisher's Linear Discriminant Analysis and adapts it for clustering. This leads to the creation of what they call a discriminative subspace. And this right here illustrates a huge shift in thinking. The old way was to look for the directions where the data spreads out the most, but that spread could just be meaningless noise. This new idea says, forget that. Let's actively search for the angle that makes the different groups as distinct and tightly packed as possible. So how do they actually pull this off? Well, that brings us to the elegant solution at the heart of this paper, an algorithm called the Bayesian Fisher-EM, or just BFEM for short. BFEM works in this really cool three-step loop. Think of it like tuning an old radio. First, in the V step, it makes a probabilistic guess, a soft guess, about which cluster each data point might belong to. Then, in the M step, it uses those guesses to refine its model, like calculating the center of each cluster. And finally, and this is the magic part, the F step uses that new model to find a new, better viewing angle that maximizes the separation. And then the whole process repeats. By cycling through these steps over and over, the algorithm is simultaneously learning the clusters and the best way to look at them. It's this powerful feedback loop where better guesses lead to a better view, and a better view leads to even better guesses until it all settles into an excellent final solution. Okay, so the theory sounds great, but does it actually work? How does this algorithm perform when it's put to the test against other cutting-edge methods? Well, the results on several real-world data sets speak for themselves. BFEM performs incredibly well. For instance, when it was tasked with identifying handwritten numbers or classifying different Italian wines from their chemical profiles, it achieved a really high accuracy, consistently outperforming a lot of the existing methods. And it also has some amazing practical applications, like cleaning up noisy images. Imagine this picture was just full of static. The algorithm would break it down into thousands of tiny patches, find all the patches that look similar, like all the little bits of a stone wall, group them together, and average them out. That process effectively cancels out the random noise, and you're left with a much cleaner version of the original image. Pretty amazing, right? So let's step back for a second and look at the big picture. Why does getting better at this kind of thing matter so much? Well, mastering high-dimensional clustering is absolutely critical for so many fields that are swimming in complex data.
We're talking about finding patterns in gene expression, organizing millions of documents, enhancing medical images, identifying financial trends, or segmenting customers from mountains of data. The applications are everywhere.
Ultimately, this work is a powerful reminder that sometimes the biggest breakthroughs don't come from getting more data, but from finding a smarter way to look at the data we already have. It leaves us with a fascinating question. As our world generates more and more complex data, what other hidden angles are out there just waiting for us to discover? Thanks for joining this explainer. And a final note, this production is for entertainment and educational purposes only.